Suppose you are given this recurrence relation and are asked to find a closed-form solution for it. What should you do? First, we need to find out if this is a first-order or a second-order recurrence relation. We can tell it's a second-order because it has two base cases and because the recursive step depends on the two previous values in the sequence, not just one. So, now that we know that it's second-order, let's take a look at the recipe for finding closed-form solutions. Step 1. Does it match the form? The recipe only works for recurrence relations that have constant coefficients, not variables. And it looks like the current example checks out. The first coefficient is 2 and the second is 3. So let's move on to step 2 of the recipe. Find the roots to this equation, t squared minus c1t minus c2. We know that c1 is 2 and c2 is 3, so we plug them into the equation and we get this. From your previous math classes, you probably recognize this as an example of a quadratic equation. There are exactly two answers called roots to this equation, and there are multiple ways of finding them. In this video, I'm going to focus on just one way to find the roots, using the quadratic formula. Check the textbook for other ways. Let's compare the general form of the quadratic equation to the specific form used for second-order recurrence relations. The most obvious difference is the change of variable name from x to t. But what other differences do you see? The value c in the basic equation is equivalent to negative c2 in ours. b is the same as negative c1. What about a? Since there is no coefficient on t squared, we assign a to 1. Now that we've found the equivalencies, we can substitute them into the quadratic formula to find the roots for our equation. First, by plugging in 1 for a basically goes away. Then we plug in negative c1 for b. So the negative b1 in the front becomes positive c1, and the b squared becomes c1 squared. Finally, we plug in negative c2 for c. That changes the minus 4 to a plus 4. And what does that plus minus thing mean? It just means that we need to compute the answer twice, once with plus and once with minus. That's how we get two roots. Now, back to our example problem. In our example, we found that c1 is 2 and c2 is 3. So let's plug these values into both formulas and see what comes out. So the 2 squared becomes 4, the 4 times 3 becomes 12. Now 4 plus 12 gives you 16. The square root of 16 is 4. So on the left, 2 plus 4 gives you 6. On the right, 2 minus 4 gives you negative 2. So the two roots are 3 and negative 1. Our textbook calls these values R1 and R2, so I'll use that same terminology here. So now we've finished step 2 of the recipe. Step 3 is to solve this system of equations to find the values of p and q. Remember that s1 and s2 are simply the base cases of the recurrence relation, which are given, and r1 and r2 are the roots that we found in step 2, so the only unknowns are p and q. So given two equations and two unknowns, there are lots of ways to solve for the unknowns. If you have a favorite way, feel free to use it. Let me show you one way, that is, to pick one of the unknowns and rewrite the formula in terms of that unknown. Let's try it. For the purposes of this demonstration, I'm going to drop the parentheses on s1 and s2, just to simplify the notation a bit. Let's modify the first equation. Subtract p from both sides, and you get s1 minus p equals q. I'm going to change the right and left sides of the equal sign because I think it looks nicer. Now we know that q is equal to s1 minus p. We can substitute that in place of q in the second equation. Now let's distribute the multiplication of r1 like this. Now let's switch places on the pr2 and the s1r2. Just move them left and right. Next, we see that p is a common factor of both pr1 and pr2, so let's pull out the common factor like this. Next, let's subtract s1r2 from both sides. Now, if we divide both sides by r1 minus r2, then we've isolated all the knowns and unknowns onto opposite sides of the equal sign. I'll put the p on the left because it looks nicer. So now I have a formula for finding p, and once I find p, I can easily find q. So back to our specific example, where s1 equals 3, and s2 equals 1, and r1 equals 3, and r2 is negative 1. Let's plug the values into the formula and do the math. So 3 times negative 1 gives you negative 3, and 3 minus negative 1 is the same as 3 plus 1. 1 minus negative 3 is the same as 1 plus 3, and 3 plus 1 is 4. 1 plus 3 is 4. 4 over 4 gives us 1. So p equals 1. Now that we know the value of p, we can plug it into our other formula for q. 3 minus 1 is 2. So q equals 2. After solving for p and q, we're ready for step 4 of our recipe. Plug all of our numbers into this formula, and that's the closed form solution. So let's use this formula for our specific example where p equals 1, q equals 2, r1 equals 3, and r2 is negative 1. So let's plug the values into the formula. We can actually drop the 1 here since it doesn't change anything. So this is the closed form solution to the recurrence relation I showed you at the beginning of the video. But does it work? Let's test it out by computing the first 5 values in the sequence like we did in the previous video. So for n equals 1, so 1 minus 1 gives us an exponent of 0. Anything to the power of 0 is 1. So we have 1 plus 2 times 1. 1 plus 2 is 3. Now for n equals 2, the exponent is 2 minus 1, which is 1. Everything to the first power is just itself. So we have 3 times 2 times negative 1. 3 minus 2, which is 1. Now to speed things up, I'm going to do steps 3, 4, and 5 at the same time. So if you look at the exponents, we subtract 1 from all of them, do the exponents as needed, we get that. Do the multiplication on the right, could either plus 2 or minus 2, and then the values turn out like that. Now, if you compare these 5 values with the 5 values we computed in the first video using recursion, you'll see that the answers are the same, but the closed form solution is superior to the recursive version because you can compute each value directly without computing the previous values first. This is much more efficient and even opens up the possibility for computing multiple values simultaneously. In closing, this video demonstrates the textbook's algorithm for computing the closed form solution for a second-order recurrence relation. Please check the textbook for additional examples.